right, it's time. Welcome back to everybody. I don't think I have any big announcements. We got homework due tomorrow, as usual, and the quiz shall be on Friday. Please continue to come and try your quiz questions if you got some that you want to try. Anyway, let's talk some more about series. We have so far been talking about basically only two very specific kinds of series, but what we're going to move into and the next several topics on the big list are in this general category. That is convergence tests. The idea is these are going to be a few different methods by which you can look at a series and tell whether or not it converges. These tests generally only tell you if it converges or diverges. They typically don't tell you what it converges to, but just that a series converges or not. As far as what we know so far, we have discussed, most of what we've discussed has been this, the geometric series, a r to the n minus 1. And this one, I hope everybody remembers the formula for what it converges to. Well, I should say this converges to a over 1 minus r when the absolute value r is less than 1, right? And if the absolute value r is greater than 1, it diverges. All right, and there's one other. So this converges to this when r is less than 1, and it diverges when absolute value r is greater than 1. And we also discussed, I believe we just discussed this last time, just the very specific example, 1 over n, that diverges. And this, I will refresh your memory, this is called the geometric series, that first one, and then this one is called the harmonic series. All right. What about other kinds of series? If your series doesn't look like one of those two things, then we haven't talked about it yet, and we don't know if it converges or not. So others are hard to deal with. There actually aren't all that many sort of nice formulas. Like this one right here, which has a formula for what it converges to, that is very convenient, very nice, and usually that doesn't happen. Like you can imagine a similar format of a series. Typically there isn't any kind of nice formula that tells you what it converges to. All right, others are hard to deal with. One other class of series that I want to mention today, which is another important type of series, is another type of series is this, 1 over n to the power p. And our book calls this the p series. 1 over n to the power p is what that says. N equals 1 to infinity, of course. This is called the p series. And depending on what the p is, it might converge or it might not converge. So depending on the p, I will say this sometimes converges, not always, but sometimes converges depending on the p. So if the p equals 1, then I'm just talking about 1 over n. So for p equals 1, I'm talking about the sum 1 over n. And this is the one that I just said a few minutes ago, the sum of 1 over n diverges, right? That's right here. So this is the harmonic series, and it diverges. All right, but what about p equals 2? That would look like the sum 1 over n squared. If you write out the terms, it'd be 1 over 1 squared plus 1 over 2 squared, 1 over 3 squared. This is what I'm talking about. 1 over 4 squared. etc. It turns out that one converges, but it doesn't converge to an ordinary looking number. It converges actually to a very strange, like these actually add up, but they converge to a very strange number. So and we're not really going to go through this, but it turns out that this value, the sum 1 over n squared, actually converges to something around 1.64 something something something, and it was worked out a long time ago by Euler. This is a big name in like European mathematics. Euler, it's not Euler, don't say Euler. You'll sound foolish if you say Euler. This is a German name, so it's pronounced Euler. Anyway, Euler actually showed that the sum of 1 over n squared actually adds up to, you ready for this? It adds up to pi squared over 6. This is a truly bizarre result, something that no one in their right mind should be suspecting. What I'm adding up is something like 1 plus 1/4, 1/9, 1/16. Those numbers, for some reason, add up to pi squared over 6. Very strange. Very unexpected, and I hope maybe you believe me now that you see this, where that I said that actually there's no really good formula for these. Like this thing I said, 1 over n to the power p converges sometimes depending on the value of p, but actually there's no formula for it. It's just, it has been worked out in specific examples sort of over time throughout history, but there is no like general formula that's known for this. For example, this was shown in, what do I got here? Sorry, my pages are out of order here. Nah, my pages aren't out of order. Let me just say, no general formula, like in terms of p. For the value of this series. But we are going to talk about for which p does it converge. That is something that we can talk about very, and there's a sort of a simple answer to that question. But what does it actually add up to is very complicated, and there basically is not a simple answer to that question that we know of even today. All right. Anyway, let's talk about our convergence tests. So we are going to talk about the first of them today, and that is called the integral test. I hope you don't mind. I said, we were done talking about integrals, and we're just going to talk about sequences and series for the rest of the semester, and that's true, although this test about series involves doing integrals. So you do have to still remember how to do some integrals to talk about the integral test. But anyway, this is a way to show that a series converges, even if you don't really know what it adds up to. A way to show a series converges. Even without knowing actually what it adds up to. This is a little weird, because when I say it converges, it means like those numbers, they actually do add up to some answer. And it turns out there's actually several ways you can show that it converges even though you don't know what the answer actually is. This is strange, but it's not that weird, all right? And in the case of the integral test, this involves comparing it with an integral. Compare the series with an integral. What I mean is, if you have something like the sum of, if the thing inside your sum looks like a function of n, you can compare that and that. All right, so what I mean is something like, if I'm talking about 1 over n squared, the sum of 1 over n squared, n equals 1 to infinity, you would compare that to the same function, but writing it now as a real valued function in terms of x, all right? So whatever the function is over here that you're trying to figure out the series of, you turn that into this improper integral. And there is a relationship between these two things. The sum over here, it is related to this improper integral. Now, they are not equal, so it's not related by an equality. So these are not the same. These are not equal. I mean, the series versus the integral, they're not equal, but their convergence is related. What I mean by that is, for example, we are going to say, what I'm about to say is not strictly speaking always true, but basically we're going to say, if this one, the integral converges, that means the series converges. And if the integral diverges, that means the series diverges. That's the idea. So the answers that they add up to are not the same, but whether they converge or not, that ends up being the same kind of. Like I said, there's actually some sort of hypotheses that are required. But anyway, I'll try and draw a picture. Like for example, for let's say the sum 1 over n versus the sum not the sum. I'm going to compare that with the integral 1 over x, right? You use the same function inside either way. All right, if I were to draw a picture of this, usually we're not going to draw the picture, but I'm just trying to explain sort of where all this comes from. Of course, 1 over x, the function, looks like that. This is f of x equal 1 over x, right? And I'm talking about the integral from 1 up to infinity. That's this area, all right? How does that area compare with the series, the sum 1 over n? Well, if you think about it, actually that series we can represent, we are usually not going to do this, but we can represent this as sort of a bunch of blocks. And I'm going to draw it like this. This block here has area 1. That's actually a square. It doesn't look like a square in my picture, but the base, the width of that thing is, from 1 to 2, so that's a 1. And then the height of that is also a 1 because I'm talking about the function 1 over x. And then the next block here, this has height 1/2, right? Here's 1, here's a half. So this area right there is a half. The next area would be a third, etc., right? So the integral is the red part, right? That's the red area. Whereas the series, the sum n equals 1 to infinity, 1 over n, is the sum of the blocks. All right? And you can tell on this picture that the sum of the blocks is bigger than the area under the curve, just because the blocks are bigger than the area under the curve. So in this case, sorry, I have to scroll the picture. In this case, the sum 1 over n equals 1 to infinity, is bigger. Greater than or equal, I'll say. Although, I mean, you can tell in the picture it's not equal. I'll just write greater than. Yeah, maybe I'll write greater than. The integral, right? That's what I'm saying. 1 over x dx. So the series is bigger. That's just because you can tell the blocks, if you add up the area of the blocks, they add up to the, they are bigger on the picture than the area under the curve. All right? But check it out. If you remember from your days in Calc 1, this is what I would call a left-hand Riemann sum. That is to say, I'm making these blocks so that they touch the curve on the left, right? What if instead I made the right-hand sum? It would look like, I'm going to use some more colors here. Sorry, I know not everybody can do colors like I can. I'll do these in green, right? This would be the right-hand sum. Those green blocks all right? And if you think about it, what are those green blocks? The areas of those blocks, they are actually, I mean, these green blocks are the same as these black blocks if you shift them to the left by 1 position, right? And just like throw away the first one. They have the same heights as these ones which I drew before in black. It's just they're moved over a bit, all right? So I'm gonna say here, the green area, this green part, it's actually, if you add those up, it's still equal to the series. It's just as if you had thrown away the very first one. In fact, that is this. This is a little weird, but the area of the green blocks is the same as the area of the black blocks. It's just the black ones include that first guy, but the green ones don't, all right? Otherwise, they are the same blocks. They're just shifted over by 1 position. And so the area of the green blocks is this. It's the series starting at 2. And the point of this is the green blocks, they are under the curve, right? All of the green blocks are under the curve. So the area of the green blocks is less than the area under the curve. This is less than integral 1 to infinity 1 over x dx, all right? So if we put all of this together, so all together, it says the sum n equals 2 to infinity 1 over n is less than the integral 1 to infinity 1 over x dx, and that is less than the sum n equals 1 to infinity 1 over n, all right? The integral is kind of in between those two different versions of the series. And here's the punchline. That means if the series converges, the integral automatically also converges. Like if this actually adds up to a specific number, and this one also adds up to a specific number, then this one has to be in between those two numbers, and so it also converges, all right? And if the series diverges, if this sum is actually infinite, that means this one over here is also infinite, and so the integral is also infinite. And so the punchline here is, this means what I just said, if the series converges, the integral also converges, and if the series diverges, the integral also diverges. This means, the way I'm going to say that is, the series and integral have the same convergence / divergence. That is to say, either they both converge or they both diverge, right? You can't have one converge and the other diverges. They have the same convergence diverges. Either they both converge or both diverge. All right. Now, in general, if I just show you a series out of nowhere, it's going to be very hard for you to tell if it converges or diverges. Not so for an integral, though. Improper integrals we already know how to do, and they are quite a bit easier to handle than series. And so the way in which we use this is, if you start with a series and you don't know if it converges or not, you turn it into an integral and find if that integral converges or not, and then that tells you if the series converges or not. This is the idea from behind the integral test. Now, I will say, as I said before, what I'm saying here is not exactly always true. It requires some special things to be true about the way that these blocks are arranged, all right? In order for this to be true, it is required that these black blocks are always above the curve and the green blocks are always below the curve. If you think about it, the reason that happened in this case is because the curve is always going down. If the curve is always going down, then this whole picture will be exactly the same, even for a different series. So I'm going to write this sort of slightly formally as a theorem here. So the theorem says, so I'm going to write this as a theorem. This is called the integral test, and then we'll do a bunch of examples. The theorem says, first of all, this only applies if the function is decreasing. The only reason that these blocks lined up in the way that we wanted is because the function is always decreasing. That makes it so the black ones are always overshooting the area, and the green ones are always undershooting the area. Now, if it was increasing, then actually you could say the same thing, but the other way around. But we're typically just going to do this for decreasing functions. That's because if the function is increasing, then the series is going to diverge anyway. Anyway, if f of x is decreasing, I wrote with a G, come on now, decreasing on the interval 1 to infinity. Decreasing, it doesn't actually, technically, it doesn't have to be always decreasing, only from 1 up to infinity. That's the only place we care about. So if f of x is decreasing as a function, this is decreasing as a real function from 1 to infinity, then basically it means that the series and the integral have the same convergence properties. So I'm going to say it in this way. If the integral f of x dx diverges, then the series f of n equals 1 to infinity diverges. And if the integral converges, then the series converges. Right. It's called the integral test because you can use this to test if the series converges or diverges. And you do this by changing it into an integral and then doing the improper integral. And the improper integral is a lot easier to do than actually trying to evaluate the series. All right? So let's try to do a couple examples here. How about, this is the integral test, all right? It just says if your function is decreasing, then the convergence of the series is the same as the convergence of the integral. So how about, let's use the integral test to test the convergence of the sum 1 over n. All right, now we already know because of what we talked about last time, this diverges, so hopefully that's going to be the answer, that this diverges. All right, we want to test the series 1 over n. So you turn this into a function. So here our function would be f of x equals 1 over x, right? And you note that this function, you know, it looks like that. It really is decreasing on the interval 1 to infinity, right? Over here is all I care about. This is indeed a decreasing function. Actually, it's decreasing everywhere, but we don't actually need it to be decreasing everywhere. All right, that means we may use the integral test. And what is it? So, so this 1 over, the series converges. I will just say the series convergence is the same as the integral 1 to infinity 1 over x dx convergence. All right, and we can just straight up do that improper integral. So we go 1 to infinity 1 over x dx, and I hope that everybody remembers how to do an improper integral like this. You turn the integral into a variable and then take the limit as that goes to infinity, and we usually call that t. So I make this lim t goes to infinity, integral 1 to t, 1 over x dx. Let's do the integral. What's the, there's no tricks here. We just can straight up do the antiderivative. What's the antiderivative? 1 over x? Surely everybody knows, yeah? It is the ln of x. So this is the natural log, I suppose, absolute value x. Plugging in 1 and t. This becomes lim t goes to infinity, natural log of t minus natural log of 1. Natural log of 1 is 0. The ln of t, as t goes to infinity, you're talking about the natural log of a really big number, which is also a really big number. That also goes to infinity. So this part right here goes to infinity, which means the integral diverges. All right? And that means the series diverges, which is what we are really trying to work with. So since the integral diverges, my conclusion is, therefore, the series also diverges, which is really what we were after. All right? This is a typical sort of easy example of doing the integral test to see if a series converges or diverges. Any questions about that one? Let's try 1 over n squared. How about the series 1 over n squared? All right. It should go pretty similarly. This is the one, remember, that Euler proved that this converges to pi squared over 6. Now, using the integral test, you cannot say what it actually converges to. It only tells you, does it converge or not. But anyway, we can still do this using the same method, the integral test. So we, first of all, observe that my function this time will be 1 over x squared. And this function looks like that, which is indeed decreasing on the range that we care about. Actually, this one is increasing sort of on the left side, but we only care about from 1 to infinity. It's decreasing. So this is decreasing. So we may use the integral test. And so instead of the series 1 over n squared, I consider the improper integral 1 over x squared. I bet she didn't think she was walking into improper integrals. It's true. We're back on that. All right, how do we do 1 over x squared? Well, okay, as always, we turn this into lim of something or other. Lim t goes to infinity, integral 1 to t of 1 over x squared. I'm going to think of that as x to the minus 2, of course. And then we do the integral. This is just the power of x, so I increase the power by 1. This becomes lim t to infinity. It becomes x to the negative 1, right? And you get a minus sign in front because I'm doing the antiderivative. And I plug in the values 1 and t, 1 to t. This becomes minus, sorry, I got my lim here. T goes to infinity. Minus t to the minus 1 minus 1 to the minus 1. All right? T to the minus 1, of course, is 1 over t. So this is negative 1 over t. And then I guess all of that just is a plus 1 at the end. And what happens when I take the limit? T goes to infinity. 1 over t becomes 0. And I just get 1 as my answer. All right. Now, what that answer is not terribly important. Really, all we care about is, does it converge or diverge? And the answer is it converges, because I got 1, all right? Converges. So that means that the series 1 over n squared also converges. All right? It does not converge to 1. The integral converges to 1. The series converges to pi squared over 6, which is not the same as 1. So just because the integral gives you some answer, it means that it converges, which means the series converges. It does not mean that the answers from these two parts are both the same answer. They are typically not the same answer. All right, great. One more example. I thought, what about 1, so we did 1 over n, right? 1 over n diverges. Then 1 over n squared. That one apparently converges. What about other powers? 1 over n to some power? Like, can we look at 1 over n cubed? I want to just see, like, is there some kind of a pattern here? Let's try the sum 1 over n cubed. All right? It's going to be pretty much the same. Actually, the graph of 1 over n cubed looks like this again, right? It looks just like 1 over x. 1 over x cubed. But anyway, when we turn this into an improper integral, it's going to be the integral 1 to infinity of x to the minus 3, right? We've just done this twice, so I hope everybody's keen on the steps. we do the integral. So this we turn into a limit, as usual. T goes to infinity, integral 1 to t, x to the minus 3 dx. And then we do the integral, we increase the power, it becomes negative 2. And then we divide by the negative 2, so it'll say lim t goes to infinity, 1 over minus 2, x to the minus 2, plugging in 1 and t. You plug in the t and the 1. Lim t goes to infinity, 1 over minus 2, t to the minus 2 minus 1 over minus 2, 1 to the minus 2. What do you say? This limit, does it converge or diverge? Con or die? It converges. Yeah, I agree. Why does it converge?
Because the t to the negative 2 just goes off to 0.
Yeah, right. This t to the negative 2, you should, again, think of that as 1 over t squared. And when the t becomes infinity, that part becomes 0. And then the whole answer ends up being just the other thing. So this right here goes to 0. And so that means it converges. All right. Basically, why does it converge? It's basically because this exponent was negative, right? If you see a negative exponent on the t, and then you plug in t going to infinity, you're going to get 0 here. So this converges, I'm going to say parenthetically, since the exponent was negative, right? That's kind of what made it converge in this example. And it's why the previous example converged also, right? In this case, I ended up with t to the minus 1, but for the same reason, because that exponent was negative. All right, so that means the sum 1 over n cubed, n equals 1 to infinity, converges. All right. Remember, if you do 1 over n squared, that actually converges to pi squared over 6. What about 1 over n cubed? Does this converge to some other weird number in terms of pi? Actually, it does not. This number converges. Here's the little fun fact. This is referred to as, it converges to something. It's what it converges to is referred to as Apéry's constant. And actually, this is just some weird number which is not expressible in terms of pi or e or anything else. It's just some other thing which has no other kind of formula for it. Very strange. The moral of the story is when you do these 1 over n to some power, you just get some weird number, and there's no telling what that weird number may be. Sometimes it's pi squared over 6. Sometimes it's just some crazy number that has no other expression in terms of anything. All right. Can we say, I would like to say something generally speaking about how can you tell if these things are going to converge or not? Basically, as I was trying to indicate here, they're going to converge when this exponent is negative, that is less than 0. So that happened here because it was negative 2. It also happened here because it was negative 1. Remember, this exponent is going to be 1 less than that because that's the exponent that you get when you do the integral of that. And because this starts off being negative, when you do the integral, it increases. The exponent increases, but it's negative. So basically, it's because this 2, what am I saying here? This ended up being negative, all right? Which has to do with the fact that that 2 is bigger than 1, because when I subtract 1 from it, it ends up still being a negative value. So generally speaking, this will work in general. Generally, if I have, the series 1 over n to the power p, this converges as long as the p is greater than 1. So this converges when the p is greater than 1. If the p is greater than 1, then when you do the integral, the p remains as a negative exponent. And so it's going to converge when you do the improper integral. All right. So generally speaking, this series converges when p is greater than 1, and it diverges otherwise when p is less than or equal to 1. All right. This is important, and this is something that you should, I suppose, have memorized, I guess. It converges when p is greater than 1, and it diverges when p is less than or equal to 1. This, remember, is what I called before the p series, and this is going to come up all the time. All right? And you should add this to your sort of list of series that you know about. Remember, I will just refresh our memory. If you have this, a r to the n minus 1, this converges when absolute value r less than 1, right? And then now you can add into your sort of bag of tricks. This one converges when the p is greater than 1, right? Now, the first of those two, actually, you have a formula for it. It adds up to a over 1 minus r. The second one, there is no formula for what this actually adds up to, because, like I said before, you just get crazy answers depending on the different values of p. Just give you essentially totally unpredictable values that it actually adds up to. I thought, would you mind a fun little story about this p series? Actually, the values, as I've said, the values here are very weird. And people for a long time have been interested in the values of this series. Like I said, Euler worked on this when p equals 2. And this other guy, Apéry, calculated the answer when p equals 3. The values are very weird, and people over time have turned this into like a function. You know, depending on what the p is, it adds up to a different number. And so you could think of this whole thing as like a special function where you plug the p in and you get some answer. And this is called, it's written with the Greek letter zeta, which looks like that. That's a very nice looking zeta. Usually my zetas are not so nice. But anyway, this is a function that is defined like this. The sum n equals 1 to infinity. This is referred to as Riemann's zeta function. That's a more typical sort of ugly looking zeta as I drew it over there. This is called Riemann's zeta function because Riemann studied this also. You know, Riemann is mostly known for work in geometry, but this was one sort of he wrote one paper about what we now call number theory, which is just about numbers, how numbers add up and such. And he called it zeta in his paper, and now ever since it's been referred to as Riemann's zeta function. And actually, this is one of the major sort of things which motivated major development in mathematics throughout the 20th century and continuing today. There are many questions about the Riemann zeta function that are still unanswered. And one question in particular, so this is very weird fact. If p is a complex number, that is to say it has, it involves, if the p involves some imaginary numbers, then actually you can make it so that this whole thing adds up to 0. So if p is a complex number, it's possible for this zeta of p to actually add up to 0. Ordinarily, like if p is a real number, then n to the power p is always positive, and so this can never add up to 0. But if p is allowed to be an imaginary number, then sometimes this can end up being negative, which can allow this to add up to 0. It's possible for the zeta function of p to equal 0. And there's this big question, for which p does zeta of p equal 0? And this is a question that people have been thinking about for a long time. Actually, Riemann, in his famous paper about the zeta function, wrote down a hypothesis. So Riemann gave a conjecture about for which p the zeta function equals p, and this is referred to as the Riemann hypothesis. And this is, I think if you ask just sort of like a random guy on the street, they will say this is probably the most important unsolved problem in all of mathematics. People have been working on this for a long time. I mean, since the time of Riemann when he wrote his hypothesis in the paper. But this is still an unsolved problem. If you ever, if any of you got any ideas, let me know. I gave you $50. There's $1 million prize associated to this question. So if you do prove the Riemann hypothesis, then you can get $1 million, which is pretty good, I guess. The Riemann hypothesis actually, you see it just mentioned like in pop culture every so often. There was actually a guy. There was a guy on TikTok a few months ago. Do you remember this guy who said that he proved the Riemann hypothesis? I watched his TikToks. I mean, I had never heard of him before this, but he sort of became temporarily famous because he said that he proved the Riemann hypothesis. His proof was just a whole bunch of nonsense, but he was temporarily famous. People often say Riemann or Riemann or something like that. This is how you know they don't know what they're talking about. There was a Law and Order episode about somebody who proved the Riemann hypothesis, and then like they got murdered because of it for the $1 million, something about this. But they said Riemann in the episode. There's a new show on Apple TV. It just came out like a couple months ago called Prime Target, I think. Just some kind of like spy show about mathematicians, but it also involves someone who has a proof of the Riemann hypothesis. For some reason, this is like something that there must be like one guy in Hollywood that people call. They're like, oh, we're gonna make a movie about math. What do we got? And he's like, oh, you gotta put the Riemann hypothesis in there. Somehow everybody has heard of this in Hollywood. Anyway, interesting fact. There's a $1 million prize on this problem, which has been offered by a sort of math research group with a bunch of money. And there are 7 problems which each have $1 million prizes associated to them that were the prizes were officially announced in the year 2000. They're called the Millennium Prize problems. And they were meant to be sort of, these 7 problems are the most important unsolved problems, and they will kind of direct the future of mathematics throughout the new millennium. That was the idea. And one of them has been solved. The Riemann hypothesis is one of the ones which is still unsolved. And you'll get the $1 million, but actually you will become sort of instantly famous and world-renowned as a mathematician if you solve any one of these problems, which is probably better than $1 million in terms of career prospects or whatever. But it also means, because of the big stature, it also means that if I was talking to my friends and I said, hey, I think I'm working on this proof of the Riemann hypothesis, they would immediately think that I had gone crazy or something, just because it's kind of like saying, I have just discovered a cure for cancer. Unless I'm already some kind of superstar cancer researcher, you should think that I'm probably an idiot if I say something like that. These millennium problems are the same way. It is, of course, possible for anybody to claim the prize, but basically, if I haven't already heard of you as a mathematician, I'm not going to believe you if you tell me you've solved the Riemann hypothesis. All right, any thoughts about that? Let me know if you got any ideas. My own research is in the area of topology, and one of the 7 problems is a topology problem, but that's the one that was solved, so I'm kind of off the hook. The Riemann hypothesis is not something that I know what it says, but I would never try to seriously think about working on it. All right, interesting story about the one that was solved. It was solved by a very strange Russian mathematician who refused the money because he somehow feels like it is beneath him as a pure academic to accept the prize money. He's not in it for the money, he's in it for the
for the game or something like that. And he's a very, like, as soon as he, in order to get the money, you have to write your proof, publish your proof in a journal, and then I think you have to wait like 5 years to make sure that there are no mistakes. Like, you want to give other people time to read your argument, and sort of everybody has to agree that the problem has well and truly been solved. And this guy refused to publish his proof. He just posted it online and sort of dropped the mic and was like, you guys, decide for yourselves if you respect this or not. And it is correct. Everybody agrees that it's correct, but he never published it. And since then, he has totally like dropped off the grid. Like he is not working anymore as a mathematician. Like, I think he lives in St. Petersburg with his mom, and I think he like teaches calculus or something at a university. But he's not into research, even though he solved the biggest unsolved problem in topology. And then afterwards, some other guy tried to publish his paper and claim the money, because he's like, hey, I can write his proof and publish it, and according to the rules of the prize, I should get the $1 million. They didn't go for that. Anyway, can we try some of these? I got 2 examples for you all to try. So remember what we've been talking about. Sorry, I went off on a bit of a mathematical tangent. It's this: if you have some series with a function in there, you turn it into the integral 1 to infinity f of x dx. And the idea is then you work on the integral, which is easier to handle because we already know how to handle improper integrals. You do the antiderivative and then see if it converges or not. All right, this is called the integral test. Your job, I would like for you test the convergence of, I got 2 examples here, n plus 1 over n to the 5 and e to the negative 3n. See what you think. Your job shall be to turn them into integrals and then do the improper integral and see if that converges or not. series. Okay. It's really one over that. But you have to do the integral. So I think it's better to keep it like that. And then write it as e to the minus 3x. Yeah, but you shouldn't put that because it's easier to do the integral. I mean, just keep it written that way. So there. I hope everybody remembers we had a integration formula like this. This is what you need to use for the second one when you do that integral. I'm going to write out the first one here, which everybody pretty much worked out already. All right, can we talk about these? So the first one, you turn into an integral, and then hopefully, everybody eventually remembered how to handle such an integral. The way I would typically write this is x to the minus 5 becomes, or x to the 5 in the bottom becomes x to the minus 5, and then I distribute, I get something like that, and then we do the integral of each of those. It's gonna be lim t goes to infinity, and then 1 over minus 3x to the minus 3 plus 1 over minus 4x to the minus 4. Plugging in 1 and t, I get 1 over minus 3 t to the minus 3 plus 1 over minus 4 t to the minus 4 minus, and then plug in the ones. 1 over minus 3, 1 to the minus 3 plus 1 over minus 4, 1 to the minus 4. All right. And then taking the limits, because those exponents are negative, this t to the minus 3 really means 1 over t to the 3, and when I make t go to infinity, that becomes 0. So this is actually kind of a general rule of thumb here. When you see negative exponents, those things will go to 0 because it really represents 1 over something which is becoming infinite, and so it becomes 0. Those two parts become 0. The last part, it just is whatever it is, and actually I don't even care what it is. This converges, right? Our job here is only to tell if it converges or not. It doesn't actually matter what it converges to, because this integral does not converge to the same thing as the series anyway. All right, so the integral converges, so my conclusion is the original series converges. I hope that's what you said. Any thoughts about that one? I mean, I think pretty much everybody did great on that. All right, and let's do the other one, e to the minus 3n. This becomes the integral 1 to infinity, e to the minus 3x dx. That is, we turn this into a limit as usual, 1 to t, e to the minus 3x dx. Do the lim, do the integral first. I hope everybody remembered that little integration rule, e to the kt, the integral of e to the kt is 1 over k, e to the kt. So this is 1 over minus 3, e to the minus 3x. Plugging in 1 and t like so. All right, and then we plug in the t and the 1. we get lim t to infinity, 1 over minus 3 e to the minus 3t minus 1 over minus 3 e to the minus 3 times 1. And you, I don't really care about this. That's just some number, whatever it is. What I care about is this. Does this go to 0 or does it diverge? The answer, again, because of the negative exponent, this goes to 0 because you are talking about something in a denominator. All right, so this, if you wanted to write out one more step just to convince yourself, this is the same as that. I don't care about the second part. And that is going to become 0 when t goes to infinity because I have something infinite in the denominator. So this goes to 0. Whatever the other part goes to, I don't care, it converges. So that means the sum e to the minus 3n converges. All right, there you go. This is the integral test. Any thoughts or questions about that? It's pretty powerful, the integral test. It doesn't always work. You have to remember what makes it work is the fact that the function is decreasing. And of course, not every function is decreasing. So you cannot always use the integral test, but for decreasing functions, it works pretty well because usually it's not so hard to calculate the improper integral. All right. That, I think, will do it for the integral test. The next thing, we got 15 more minutes. I think we can start. I'll give you a little introduction to our next topic, which is called, it's another test. The next one is called the comparison test. And actually, there's a few variations, so our book calls this the comparison tests. There are a few simple variations on the basic idea of the comparison test. So the basic idea here is to test convergence of a weird series, compare it to one we already know. That's the idea behind the comparison tests. All right? To test the convergence of a weird series, compare it to one that we already know. And by compare, I mean using inequalities. Compare using inequalities to one that we already know. Rather than giving you, so I'm going to write this as a theorem again, but maybe I'll save that for next time. Let's just do an example. I think it's a pretty simple idea. It is a little tricky, so in my opinion, using the comparison test is harder than using the integral test because you do have to have some kind of idea on your own sometimes rather than just verbatim changing the thing into an integral. But for example, here's a typical example that I have in mind. How about this? All right, this is a weird looking series. So this is not by itself, this is not a geometric, and it's also not a p-series. And those are basically the only ones that we know about. Like I said, my strategy is compare it with something that we already know. That's what I said up here. What are the ones that we already know? They are these. AR to the n minus 1 and 1 over n to the p. All right, those are the ones that we already know. And we know, I mean, you should have these memorized eventually. We know the first one converges when absolute value r is less than 1, and we know the second one converges when the p is greater than 1. But anyway, what does this look like? Well, it doesn't look like either of those, but I would say to me it looks more like this one, the p series, than the first one, just because I mean, I see something like 1 over n's here rather than n inside the exponent. I certainly don't see anything like that here. So to me, I'm going to say this looks like a p series. That's the second one, right? This is the p series. The first one is the geometric. So when my intention is to compare this to some kind of a P series. It looks like a P series. Now, what is the P, like the power being used here? Well, I see a third power. I also see a power of 1 here. It turns out, we're going to learn some general principles here, but it turns out you should kind of focus on the highest power here. So I'm going to say it looks like a P series with P equals 3. So my comparison will be the sum of, this weird thing that I have to begin with versus the sum 1 over n cubed, all right? And I'm going to try to compare them using inequalities, all right? And this is the hard part. I mean, once you have the idea of how you want to make your comparison, you have to actually play some simple tricks with inequalities. And this, if you're not used to it, can be a little strange. But here go some simple tricks using inequalities. N cubed plus 3n plus 7. So I am going to use inequalities because I know how this is going to work out. I'm going to use less thans. Now, I want to change this around to make it look like 1 over n cubed. And the first trick I'm going to do is, with a less than, I'm going to just throw away the 3n and the plus 7, all right? Why did I just get rid of those? Just because I want to? The answer is a kind of yes, just because I want to. I'm trying to make it look like this, and you should be asking yourself, is it really true that this one over here is less than this one? And you have to think about, what did I do in this step? I made the denominator smaller, and that makes the fraction bigger if you make the denominator smaller, all right? So this, I remember the first time I was doing problems like this, I found it extremely confusing to tell, is this inequality, should it go the other way around or should it go this way around? Why that's true is because I made the denominator smaller, so it all gets bigger. All right? I made the denominator smaller by just throwing away the 3n and the plus 7. And that means the whole thing gets bigger, and that's why I used the inequality sign going in that direction. All right? That's the end of my sort of big idea. Just one more step. How can I make this look like this? Now you might say, can I also just like change the 2 into a 1? But actually changing the 2 into a 1 will make it smaller, but I'm trying to make it bigger every time here. You don't have to do that. Actually, we can sort of sidestep that by just factoring the 2 out. Remember, you can always just factor, constant can be factored out of a series. I could have actually factored the 2 out at the beginning. Either way. All right, anyway, this is now 2 times 1 over n cubed, and this converges. That's because it's a P series with P equals 3. And remember, the P series converges whenever the P is greater than 1. All right? So what have we said throughout here? The thing that I started with is actually less than something that converges. That means this thing also converges. It can't like go to infinity because it's less than this, and this does not go to infinity. All right? So that means, so this 2 over n cubed plus 3n plus 7 is less than something convergent. So that means what I started with is also convergent. This is the idea behind the comparison tests. You start with something weird, you do some inequalities to it to change it into something that looks familiar. And then based on whether that thing converges or not, you can say whether the original thing converges or not. All right. This is the comparison test. Maybe I'll leave it at that. So next time I'll write it a little bit more formally, and then we'll do a bunch more examples. All right. I think that'll do it. See y'all tomorrow. Let me know if you got homework questions.